We are currently waiting to go live. And we might have the stream going. There it goes. All right. Welcome, everyone. I'm Mark, and I'm here to void a warranty. And today, we're continuing the computer teardown. We're going to see what's inside this baby. That's right. The DVD writer. Should be fun. This is all by HP, or at least it's branded HP. I don't know if they make it or they farm this out to some factory and do it, but we're going to see what's inside. And right now, to do that, I am looking for case screws. I don't believe this one to be a useful case screw, but I know it's nothing I need. So we're going to get rid of that one. I think these just hold this back bracket on and allow it to be secured in the machine. So with only one visible, it's got to be hiding under here. They can't have just used one tiny screw. There's something in here to see if you void their warranty, I'm sure. Feels like the motor spindle. I don't know. Let's see what we got. Oh, we've got bits that are turned down. So what I'm looking at are these little tabs. Those are the other mechanical fasteners that we have to deal with here. And I'm going to see if I can't pop those with a small flathead screwdriver. Okay, those should be bent back. I'm just looking for more. It looks like it captures in a few other spots. But once we get rid of those, it might just open up. Let's see. I'm going to have to Hulk smash, maybe. Yep. Mark Hulk smash. Oh, check that out. It's full of sick tunes. And it's written. I wonder what was on that thing. Oh, I bet you I know what was on that thing. That was probably the Linux distro that I loaded on there. All right, so we have our CD writer open, and it's nothing all that exciting yet. You know, we've got a motor in here that the CD attaches to. Right? We've got a really tiny, you might not even be able to see it until I get on the microscope, but we've got a really, really tiny focusing lens that's kind of balanced in there. And then it'll travel back and forth on a track. So as the CD spins, this moves in and out very carefully. It's very well controlled. And it picks up all, you know, all these millions of grooves that are in that track that we may or may not be able to see. We've got microscope vision at the moment. I mean, whatever we're looking at, it looks cool, but I think there's so much diffraction. I mean, it certainly looks cool. We've apparently have some interferometry going on at the moment. But I don't know if I can pull up anything. There's a barcode of some sort, but that's along the inside edge. That's the separation between what is written and what is not. I just don't seem to be able to pick up any of those lines with this setup. That's disappointing. Huh. I don't know. We tried. Next. let's see what it takes to get into this bad boy. And it looks like it is held together with just some bent edge fasteners. So I'm going to get under those, and I'm not going to get under those. I spoke too soon and I jinxed it. Well, if you'll excuse me here, I'm going to go off the camera so I can get under these things a little more and do some more Mark Smash. If you haven't heard me say it before, I always say that you should take apart your old electronic items, and you should do it in your workbench area. See, the general idea is that when you destroy these, it strikes fear into the hearts of your other electronics, so that they're less likely to misbehave later. I don't know if it works or not, but it sure makes me feel better. All right, on our down cam, I just ripped that off. It was designed to come off, probably just not the way I did it. We've got a spring plunger on the back end, so when you press it, this is what allows your compartment to pop open. It's on a sliding rail. It's actually a double sliding rail. I just lost one of the sides on that one. So this gives you your extension. And it's just a little piece of plastic, a little piece of metal, and then another little piece of plastic. And here's your spring plunger again. Nothing too exciting there. Backside does look cool for the spring plunger, but it's just you know, like a 1.5 2 millimeter rod with a spring attached to it. Okay. Off we go. More screws. I don't know about you, but I am having fun. I don't know who's watching these. I don't know if anybody's watching these. But maybe somebody is. Maybe somebody's having fun. Again, the whole idea is that maybe we can learn something once we get these things apart. Something that we can apply to our future electrical engineering jobs and tasks. Okay, well, yeah, we've got some flexible PCBs in here to look at. Those are fun. Raise your hand if you've designed one of those. Also, I'm periodically checking the chat, so if whoever's listening out there in TV land wants to ask a question or something, ask it, and if I notice it, I'll answer it, and maybe it'll be the right answer. You never know. Okay, so now we're into some meat and potatoes. Took a minute, but here we go. We've got these guys, right? This is some of the thinnest stuff around. It's looks like a piece of Kapton tape with like 1/4 ounce copper. The way that they get this copper, I mean, there's two ways that they make copper: electrodeposited and rolled annealed. Rolled annealed is like you would make pasta. You know, they just keep putting it through rollers, heating it up because copper work hardens, and cooling it down. That's not how this was made. This copper was made by being electrodeposited onto a drum, a slowly spinning drum. And this is like 1/4 ounce copper. It is thin. The grain structure is such that it can handle bending and moving back and forth and back and forth and back and forth. You may not have known this, but there's lots of different types of flex material. Some of it you can only bend 1 or 2 times. You know, it's just for assembly. This is meant for continuous use. This is the type of design that you'll see in camera lenses, anything that has a multi-bend job. And, there's a variety of lines here, some ground returns, some power, because they're thicker, you can tell. The little tiny ones are most likely signals. Here they seem to have run 2 signals between guards for whatever reason. But I think that stuff's cool. So if you ever do need something like this, infinite bend, flat flexible cable, it pays to talk to a company that, a fabricator that's experienced with these. Don't mess with the contract manufacturer. Go straight to the fabricator. Royal Circuit Solutions has a shop in Hollister, California that we use. No, I'm sorry, that's the rigid shop. The flexible one is in Santa Fe Springs, and I think there's a new one in Huntington Beach. But what you want is an old timer. You want a graybeard, somebody that's built, hundreds of thousands of boards in their career. Those are the guys you want to talk to. And for us, it's a guy named Bob. Bob is really, really, really smart. I like Bob. He's a hard worker. Only trouble is he is so busy, I have trouble hanging out with him. Wish I could do that more, learn more. But that's how it goes. The talented people are utilized. So Bob, my friend, if you're watching this and I'm looking at the stream numbers, and I know you're not, but when you watch this, if you see this, I hope you're well. It would be good to have lunch sometime and learn from you a little. I am just continuing to take things apart. I want to see more. We're going to get this under the microscope here in a second. We're going to get all the boards free first. I'm not being particularly careful about how I retrieve them. And that is because I don't want to spend the time to do it since I'm not putting this together again. I've got extras. I don't need more extras. And this is an older one anyway. The newer ones are faster. It's funny, laptops don't come generally with DVD or any optical drives anymore. Heck, they barely come with USB, full-size USB connectors. I got one of the last ones, I think, on my last laptop. It's got USB-C, which is great, but a lot of my accessories are USB-A, so then you have to plug in a dongle, and then it's just a pain. Okay, there is our, let's see where I can get that on screen. There's our stepper motor free. One stepper motor, that's the drive motor. That spins the DVD/CD around. And then we've got a second stepper motor that is a high precision. Okay, so that's our case. We don't need that anymore. So we've got a second super high precision, I believe that's a ball screw, is that a ball screw drive? I don't know. I don't really know. I don't think so. I take that back, it's not. But these little guys are what's responsible for positioning the laser across the CD surface. And it is just a stepper motor, and it's got this little tiny screw mechanism that corresponds with something over here that captures that screw, and then these things together move. Now, how does it position, right? How does it maintain it? Well, inside the lens, there's a little bit of diffraction that goes on, and an optical sensor that can sense that can keep things aligned. So as it spins and, as it goes out conically, the feedback mechanism comes from this. So it's a little more complicated than just a simple stepper with, an optical encoder on the side. To get the level of accuracy they need, they have to go through here and look at diffraction patterns. So that is a tiny motor. That would be fun to repurpose for something, but man, I don't think I'm good enough to solder on that anymore. That would definitely require the microscope. I'm getting old. Okay, before we tackle that, this is the motor. It is, I mean, that is a low profile baby, and it spins fast. You know, I don't know the rotation rates on CDs or DVD, but man, it's a lot. And if you look closely, you can actually make out the various coils underneath there that are activated in turn to spin this thing up at precise speeds. So, I don't know, is there any... I'm sure this is press fit together and there's probably nothing I can do, but let's grab it with pliers and see. Guess we can go back on single source here, or multi-source. Yep, it's going to be press fit on. I'm not going to be able to easily extract that. Oh well. All right, let's move to the microscope and get in touch with this optical setup. So, this is a focusing lens that is on a spring mechanism, and it's got coils. So what we're looking right now is we're looking at one of those coils, one of those movement axes, and that's what it can use to focus and make adjustments. So you can kind of, I mean, if you know what you're looking for, you can make it out. That doesn't do you much good. But you can kind of make out the way that they have this thing set up. Like right now, that metal bar at the top is a little bit of a alignment and a spring mechanism for return. Got the same thing down here. So by powering those coils of wire, they can control how high up and down this thing needs to go, so it's the perfect distance from every DVD. That's their feedback mechanism. And I don't know what level of variation exists that's required, but they designed it, so it must be a problem. Then over here, somewhere, there it is. Is it? Right. Looks like there's it could be a connector. My view's obfuscated at the moment. Oh, maybe that's just a connector. Okay, I thought we had an IC on board. All right, I think at this point we're going to have to peel back some layers of the onion. Everything else is covered. So, going to do a Mark smash. Those of you listening closely will hear the calls of Chester in the background. He's saying hello to you all in TV land. Okay, so here we are with our super thin, flat, flexible cable, and we're trying to make out on this little optical setup how this stuff is terminated. Hopefully we'll get there. Might have to do a little more Mark smash. So let's get off that camera for a moment. Oh! Mark smashed a little too much. There's a mirror, or could be part of the diffraction mechanism. Wow, that stuff is small. I'm destroying this, by the way. There's no way this stuff goes back together. Okay, but we can see it all a little better now. And that's what's important. To the microscope. There is this tiny little piece of glass that I'm looking for. There it is. Now to get it centered, hopefully. Come on. Oh, there it is. So this appears to be some sort of dichroic glass that I broke out of there. Probably part of the interferometer setup, but I'm not entirely sure. All right, so now we get a better view of that adjustment mechanism. So we've got the lens, and if we look at the lens from the side, you've got these metal wires that are acting as spring guides to align that lens and give it some back force. And then while that's working, there's these coils, and I'm looking for a good view of it. I just don't have the depth of field. Okay, I don't know if I'm going to be able to illustrate that. But anyways, there's these coils that get energized. I can see them with my naked eye, but I can't really show them here. So one of the issues is that this microscope is only, I don't know, a couple millimeters off the desk. I have trouble manipulating things inside of it. You can kind of make it out, kind of not. Sorry, guys. But anyways, that's the lens mechanism. You can see it can shift left and right. It's got a little bit of vertical movement too. It just gives you that microfine adjustment that you need, apparently. So very interesting stuff. Now, here's the other interesting stuff. The control electronics aren't on a circuit board. They are on this impossibly thin stuff. See, a lot of people, when they hear flex circuit board, right, they think cables. But you can actually mount parts right to it. And if you look, you can see a little bit of a fillet there. So they've epoxied this just to give it a little extra strength. But this is connected right to that impossibly small flexible cable. If you ever need to order a flexible board, you should learn the difference between flex, rigid flex, and flex with stiffeners. Flex with stiffeners is always cheaper than rigid flex. So if you can do that, if you can get away with it. So what we're looking at right now, it appears to be the laser diode. That little tiny thing is what shines the light. That could be an optical sensor too. I don't really know this design well enough to tell you. Let's see if we can see anything that looks. There's our optical sensor. That's, I wouldn't put a lot of money, but I'd put money on it. That is the optical sensor for the setup. So the laser light hit that little piece of glass, bounces into the CD, goes through the focusing lens, bounces to the CD or DVD, comes back out, and then it hits this little guy right here. Oh man, I wish I had a much closer close-up of that, but that sure looks like an optical sensor to me. There's a company out in Texas called TAOS, T-A-O-S, Texas Advanced Optical Systems, that makes a lot of the stuff, a lot of really cool sensors, and their technology hasn't changed that much in the last couple decades. They did get purchased by AMS a couple years back. Oh, but man, you can see the bonding wires. That's fun. Those little thread-like things are what connect the IC die in the middle to pads and little copper frame there, and from there it gets broken out into the rest of the board. That is neat. I want a picture of that without my fingers in it. Ha 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 ha. Let's see if we can do a little better. And then I don't know if this will work, but I'll do a little side illumination with the flashlight and see if that does us any good. I don't know if it will. We've got like 12 different color temperatures here. My friends in the video business would probably be shaking their heads at me right now. But how cool is that? You can see the bond wires, you can see the IC, you can see, well, I guess you kind of have to know what you're looking for, but you can, oh no, there it is. Okay. Let's go for broke and see if we can't zoom in on this. And you can actually make out the sensor elements. If you ever watch any of the CSI movies and they say enhance, this is totally what they're doing. And I'm kidding. They're not. They can't enhance. Okay, we've lost our location, but we might be able to zoom in now. I don't know. Come on. Did we do any good, or did we just make it radically decreased my depth of view? Am I even looking in the right spot? There we go. Okay, I guess that is bigger. Stop it! There. Oh, this is getting mad at me. I'm going to have the world's tiniest depth of view once this is done. Okay, this is big. A little out of focus, but... Okay, so now we can really make out those bond wires. We can make out the IC. It appears that those black things in the middle are the sensor element, but I want to get a little closer to know. Let's keep going. Let's go for broke here. Check that out. No! Ah, I need a microscopic stage. Okay, let's see if we can't take that for our success. So you can actually see the silicone chip die there that they've created, and you know, by combining in the proper atmosphere, you can actually get some different materials to sublimate and stick to the silicone surface, create these impurities, and you know that ends up being everything that we have that are chips, that are ICs. And then we did these bond wires, and those bond wires go out to lead frames, and you can actually see that here, since this is a transparent epoxy chip. And there's a little set of, I really have no way to point to this, this is unimaginably small, but you've got a little set of 6 dark black boxes. And my guess is that those are the sensing elements. And if we, no, I don't know if I want to do this or not, but we're going to try moving over to the diode and see what we can see there. Boy, I tell you, solid state diodes, there we go, are something else. All right, it's about as good as I can do for you. So you can see that we've got 3, 4, 5 bond wires going in. There's a good chance that, I mean, I would guess, and this is, I hate guessing like this, but I would guess, you know, that they doubled up power and ground. I assume it's a pretty high output device. And then they modulate this in some way to control the output power. how they do that, I don't really remember. But this is what's sending the pulses to the laser and that are getting bounced back, and it's figuring stuff out. And by cranking up the power, they can actually melt the plastic and do a little more damage. Let's see if there's anything else. There's a metal bracket that I broke. That's about it. But man, if you ever wanted to design something like this, believe me when I tell you, you don't want to talk to a contract manufacturer. You want to go straight to the fabricator. Eliminate the middleman, because the design rules for this are different than most of the engineering work that people do. That was neat. I don't know who was around to see that, but looking at those optical sensors is certainly pretty cool. And then I don't think we're going to be able to see anything on that laser lens. So I think that's about it for the CD. I think it's pretty well thrashed. We didn't really look much at the circuit boards, but I don't know how much there is to look at. We can see if I missed one. Oh, there's the other one. I guess while we're here, who needs lunch? We need to learn. So give me a moment, and I am just going to retrieve okay. Oh, there is some interesting stuff here. All right, let me zoom out on camera 5. What am I looking at? So here's our board, and you can see all sorts of parallel traces cruising around this thing. We've got vias. Something that I probably would have liked to see, and I recommend always, are teardrops on your vias. If you look at, okay, so we've got 2 vias in center screen right now. And if you look at them, you'll notice that they're not exactly perfectly centered holes. That happens all the time. Layer shift, drills wander, all sorts of stuff happens. So if you can teardrop your vias and that drill wander comes towards the edge where the via is, and you've got the teardrop, you don't have to worry about breakout. So that's a real handy thing. So whenever you can, teardrop. Another issue that you have with running signals this distance all next to each other is crosstalk. You want to watch out for that. But I'm guessing since this thing worked, crosstalk wasn't a problem, so I'm not going to give them crap. I don't know if you can follow this copper pour, but if you look here, they tied it back down to the lower layer. Reason that you do that is if you don't, these things become radiating elements. Probably there would have been, up here somewhere would have been another good spot to put in a couple vias, again, to tie back to ground. You can see that they did it in certain spots and not in others. Here's an interesting thing that I actually like to do. You can see 2 vias on one net. Well, if you have a problem with one via, the other one's going to handle it. This gives you a low impedance transfer. And if you look at that one at the left, it looks like it almost broke out. So good thing that they had some wide traces there. Otherwise, they could have lost that second via. Here we've got a via fence. Why, I don't really know, but it looks like they're starting to deal with some high-speed signals and they're getting a little worried. 6 vias, a 6 via tie over is a little bit of overkill. Here we're seeing a wander, and the reason that we have wanders is to increase the length of the trace. So they must have done that for a reason. The thing that I don't get is why we are wandering with such thin traces. Is that a resistive? Is that maybe that's not a wander, maybe that's a resistor they made. I think I was wrong. With that thin trace down, I think they were making perhaps a termination resistor. You might hear my friend Chester in the background informing me it's lunchtime. Okay, one of the neat things about this board, and I'll go back to this side. If you look at the back, no silk screen, nothing, no parts. It's just blank. That saves on assembly cost. It's much easier to just assemble one board. You can see some spots here that they use for test points. And typically what they would do is they'd find two holes that are pretty far apart and they would index off of those. Maybe they can do this hole in that slot. I don't know. And then on this side, the only issue is that we've got test points on the back side. Let's see if I can find one or two. And then when we flip it over, we have test points on the front side. That makes for some complicated jigging, and that does increase your cost. If at all possible, keep your test points on one side. Now that's interesting. We are at the connector. There's the solder, and here is some leftover flux, and it's cracking, it looks like. That doesn't look like it's part of the board epoxy. It can't be. So a lot of people don't want to pay to wash their boards. It's a cost-saving measure. And they use this stuff called no clean flux. Well, no clean flux, the acidity might die over time, so it doesn't corrode your parts. But even if you have no clean flux, it does not mean you have a no clean board. Ask my friend Mike Conrad about that. All the debris and everything gets left behind. But the weird thing is this is a very clean board. So why there is flux left behind on a otherwise clean board, I don't know. Maybe they did some rework after QC. There's more flux. Huh. I don't know. But they put all of their silk screen, all of their parts, and everything on one side. The only comment that I would have is if you notice programming test points. Let's see if I can pull them up for you. On the bottom here, come on. Now, I'm not looking for fiducials. Am I in the right spot? I really need to zoom out right now, I think. Maybe I'm not where I think I am. Give me one moment. I'm looking at white spots on the screen, and I'm looking at copper pads, well, blurry copper pads in the middle of my scope. Is this them? No, that's not them. Where am I on this board? Okay, we are giving up and going back to this one. I need to work on that, my microscope skills a little more. That was just giving me grief. But what I'm looking at is right here you can make out a series of 4 programming test points, okay? And the rest, you've got these tiny, tiny ones back here, which is a little bit of a problem. it makes jigging difficult, very difficult. Okay, so the interesting thing about this board was this stuff. The really, really thin, I mean, if you want to learn about this type of stuff, I would talk to Bob at Royal Flex or Chris Hunrath at Inselectro. But I would just bypass your contract manufacturer completely. And a lot of times the engineering services are free. Sometimes some companies have you do a retainer, but like Royal, it's free. That's why I like working with them. So anyways, with that, my name is Mark from Advanced Assembly. I am causing trouble here with my new little microscope setup. Hope you liked it. Hope you learned something. If you have any suggestions for teardowns, or you have any suggestions on how to make this better, let me know. I started this series yesterday. I'm sure there's room for improvement once we sit back and look at them. One of the things I particularly like is the harsh lighting. Isn't that great? Yeah, that's something crazy. I've got like 5,500 Kelvin temperature on that, like 7,200 Kelvin on the ring lights. You know, the room's at like 35. It's all over there. It's a nightmare. I'm not even going to try to fix it. I don't know how. So I hope you guys liked it. There's other videos in this series. I took apart a laptop. There's not much left. It's just a series of boards and chips and parts that I've broken off. So hopefully you liked it. Maybe it's something that you can sit down and watch while you're eating lunch. It's certainly nothing where you need to take notes. It's just me having fun. I appreciate you guys coming, and hopefully I'll see you next time. Take care.